Okay, we are ready now. Okay, so now it will be a more formal discussion about differential forms on manifolds. And for most of the part, we will follow the same reasoning that we did for vector fields. For vector fields on a manifold. Okay, so let's see. So take a smooth manifold, and roughly speaking, at this point we can think we're going to define one forms. Later, it will be apparent why do we care about one forms and not the other ones. So the whole idea of a one form is that for each point of the manifold, we assign a vector in the dual space, like we did for a vector field. At each point, a vector, but now a vector on the dual space. And the second thing is a smoothness kind of thing. The assignment of a vector for each point is required to be smooth. And one way of ensuring that is if I take any vector field on the manifold, if I contract, I get a function from the manifold to the reals. And I will require this function to be smooth. So that's more or less what we will call a one form. And so later on, we will make a different approach, which is extremely useful. Now, this is also something that we discussed yesterday. So take any smooth function, and we're going to define the differential. Again, I would like to emphasize, at this point, all of this is a single object. Later, we will see that it is the differential d applied to a function. But at this point, it's a single object. So given a function, we define a one form. So if I take any vector, this should give me a real number. And it's precisely this. This is a derivation at p and a smooth function. So that's what we will call the differential of a function. Okay? So that's a very particular one form that we get from a function. Note that we know very well that this is smooth. The function is smooth, the vector field is smooth. This function from M to R is a smooth function. So this is a one form on the manifold M. Now, so let's recall what we know from Euclidean space, and that will give us a local description on one form. This observation is exactly what I said before. This is notation. Later on, they will change, and just to make it clear, will be like this. An operator applied to a function. but that will become later. So far, we only have that one form, df. And now, actually, what we defined a few moments ago is exactly the same as the notation that we studied a long time ago. Okay? So I have a function like this. The differential of this function, f lower star, will go to the tangent space to the tangent space. Right? Now, so this is supposed to be a vector on the tangent space of R. And that vector is given by this number. So this is supposed to be a number, and this is the vector, you see? I'm using the canonical chart, X, and I have here evaluated at this. Okay, so let's prove this. So again, by the definition of f lower star, I have a vector here. And because this is one-dimensional, and I have a standard basis, which is just ddx, in order to determine this, I need to determine only a scalar, a real number. So this is what I need to find. This is one dimension using the coordinate chart x by itself. So how do we determine the value of a? This is something that we have encountered several times before, and we just evaluate on the smooth function x. So a is the same on this derivation. We have to evaluate it on this smooth function x, right? Now, on the right-hand side, it is something that we learned a while ago, and let's use that definition. Okay? So we use this relation on this equality. I have to evaluate on both sides of the equation on the function x. And then the definition of this. Right? Now, f, let's try to understand this. F is a function from the manifold to the reals. X is the coordinates on the manifold R. And that's nothing different than the identity X. Thus, I have this, right? Because X is given by the chart on the reals here. So I get this, but this is precisely our definition of the one form df. Remember the definition here. X of f equals dfx. And there it is. So this real number is this. And that's what is missing here. Okay, so again, this is something that we saw for any smooth function between manifolds m and n, and in particular when n is the reals, we have this relation. And so far, this only holds on functions of this form. Right? Okay, then, so this is what we know. And well, again, that's basically why we use the same definition, differentials of the function f, either df or f lower star. Right? Remember that once that we have charts, this is the Jacobian matrix. So that's the same as this. Great. So now let's justify what we saw yesterday regarding the dual basis. So let's consider a smooth manifold M, and everything that we're going to say from this point on is only on the chart U. So I will have a chart, x1 up to xn, and now Salvador is coming. So Salvador is coming 14 minutes late. So I mean, he's studying mathematics, and there's a big difference between 5 and 14 minutes.
For the record, the 5 minutes was my estimation.
But I mean, he was supposed to be 5 minutes before the hour, so he's actually 19 minutes late, not 14. Oh man. Okay. So we have here this chart, we have coordinates. And let's first review what we know. So for any point on the manifold, not any point on the manifold. For any point on U on the chart, we have these vectors, and we know very well that those vectors are a basis of this vector space. If we take a different chart, we will get different vectors, and we even know what is the transition matrix between those two. But for the time being, we only care about a single chart. So that's a basis now. And also we have seen that the coordinate functions are smooth functions. Of course, not on all of M, but only on U, on the chart U. And we also know that since this is a function and this is a derivation, we know what is the relation between those two sets. So, first of all, we take this as in the definition above, and because these are functions, real value functions, they are smooth, we can talk about these one forms. That's the definition that we had from the beginning of the class. And then let's use that definition, right? This is a single object, and we saw that our definition of that was a one form. If I plug in a vector, the definition that we gave was the vector applied to the function. But now the right-hand side is where we use the derivation and the function. And that we know very well what is equal to. So these objects that we defined at the beginning happen to be, these are covectors. And by this relation, they are a dual basis. This vector space has the same dimension as its dual, and moreover, because this collection of covectors or one form satisfy this, these elements form a basis. Okay? And this is just a summary of what we have discussed. Once that we fix a chart, we have coordinates. You know this very well. The xj are smooth functions, so then they find a one form. And it happened that this is a basis of the dual. Okay? And we have it like that. And so this proposition is more or less the reason that we start by defining first one forms and we don't do it in general or definition of K forms. Because these elements are going to be our building blocks to give a general definition of K differential forms. Okay, so I think that's the importance of this result. This is going to be our building blocks. Again, that's why also we make this definition. So the whole purpose of this definition and working with one forms and not arbitrary K forms is to have these one forms and they will be our building blocks. Okay? Great. So now that we have, oh wait, also here I wrote TPU, but keep in mind that it's the same if I write TP of M. Right? Because U is open. TPU is the same as TPM. If I have an open set on a manifold, the set of derivations is the same either for M or for U. Okay. So let's move on. So the previous proposition helped us to have a local description of a one form on U. On U, a one form will take this form. The coefficients are smooth functions. So if I have a one form on M, I take a chart, and that's the local description of the one form. So we are doing basically the same when we consider vector fields. If I have a vector field here, and then when I take a chart, the vector field at a point looks like this. Okay, so this is the analog. And when we study vector fields, most of the thing that we did there, we will do it here as well. In terms of constructing differential forms, the tangent bundle, and all of that. That's what I mean. But vector fields and differential forms are very, very different from the point of view of the geometry and mathematics. What I'm saying that we will follow the same ideas just to construct the tangent bundle, similar bundle, section, and all of that. Okay, now this is the general framework for a one form on U when we have coordinates. But now let's take a function, a real value function. As we said before, associated to F, we have a one form. Well, let's try to describe this one form in terms of this, meaning what are the coefficient functions? So first of all, we know that this form looks like this. So what are the functions fi? And we do the same trick that we did for vector fields when we were interested in determining this value and all of them. So let's evaluate on both sides on now not a function, a vector or a vector field, right? Because this is a one form, which is an element in the dual of the tangent space. And then I evaluate at a vector, I get a number. Now, remember that we have seen this function evaluated at this vector is 0. All of them are 0 except this one. It is 1, and that's why I have f1. I'm using this fact, okay? Now, using the right-hand side, I will get the f applied to this. Now, let's use the definition of this one form. Remember? And this is precisely this, right? Okay? this. No, sorry, this one here. Is the vector field applied, or the derivation applied to the function? And that's exactly what we are using here. The f and the vector. So it is the vector applied to the function, right? Hence, we were interested in this one form, given a function, I look at the f, and it looks like this. This one form looks exactly like this. Okay? F is a smooth function on U. Right. Are there any questions? Okay. Now, so let's describe the cotangent bundle. Remember that we have seen the tangent bundle, and now we will construct the cotangent bundle. And we follow the same lines and the same arguments that we did for the tangent bundle. So first of all, as I said, the cotangent bundle is the collection of all of the dual of the tangent spaces. So this is the definition. Just as I said, the collection of all the duals for each point on the manifold. So far, this is only a set. And from the definition of the set, we have the canonical map to M, the projection. And I mean, just to not have new notation every time, I will use the same letter as before, pi. Okay? This is no longer the tangent bundle, it is the cotangent bundle, but I use the same letter. Okay? So this is a manifold, this is a set, and this is a function. We will make this into a smooth manifold, and this will become a smooth function. So the way to make the cotangent bundle into a manifold, first, we need to give a topology of that set, and it will be given in the same way as we did it for the tangent bundle. And then after that, we need to construct an atlas, and then we will have that it is a smooth manifold. And this is exactly the same line of ideas as the ones that we use for the tangent bundle. Okay? The dimension will be twice the dimension of M. And this is a brief review of how we constructed this as a manifold and how do we give the manifold structure here. So for the tangent bundle, first we consider a chart on M because M is a manifold. We use this and we also use the function phi. So this is the map, this is the chart. And we give a topology to Tm, and Tu happens to be an open set. Remember what Tu is? What is Tu? So I do all of this, right? But remember that U is open. So TPU is the same as TPM. So I'm looking at all of the tangent spaces, but only when P is in U. And using the fact that this is a chart on the manifold, we were able to define this homeomorphism. Because on U we have coordinates, we know very well the description of any vector here. So an element here is of this form, is a point and a vector, and we're using the coordinates x1 up to xn. After that, so the map is given by this. I only consider the coefficient of the vectors. And that's how we define the charts on Tn. So the collection of charts where of this type, where U is a chart on M. Okay? So this is a review of how we define the smooth structure on Tm. Now, on the cotangent bundle, it is the same. I have the same chart on M, and now I have to define a map here. But this is the cotangent bundle on U. The good thing is I have a clear description of the elements here. So it is a point and this vector. So the function is very similar as before, like this, but now those coefficients correspond to the covector, not the vector. Coefficient A1 up to AN. And here we know that this has to, that space has dimension twice the dimension of n. Because this n comes from the entries of this vector, and this lies also in Rn because it is a chart of the manifold M. Okay? So that's how we constructed this in same argument to construct the cotangent bundle. Right. Any questions? Okay, so now we have that the cotangent bundle is a smooth manifold of dimension. The projection map is smooth. Moreover, if I take a point here, what is the preimage of that point?
The dual of some in space.
The dual of the vector space at P. So, and that happens for any point. So, for any point on M, the preimage has the structure of a finitely dimensional vector space. So what we have, in fact, it is a vector bundle of rank n. So this is a vector bundle of rank n, the same dimension of the manifold. Okay, and now when we have a vector bundle, we have sections. The space of section of a vector bundle moved the other way around are smooth functions that satisfy this condition. That's the definition of the sections of a vector bundle. And what is this? Together with this, a point here, it is assigned a vector precisely at Tp of m star. In other words, the space of sections, it is the same as the space of one forms. So the sections of this vector bundle are the same as the one forms. In a similar way, for the vector bundle, the vector fields are the sections of that vector bundle. So this is the global element, a one form. But if we have a shard, then at least in that open set, when we have the shard, we have this description. So this description of the one form is not global. It's only on the set U of the shard. So this is the global description of a one form, and this is the description on the shard U. Great. Up to this point, any questions or comments? Moises?
Good.
Okay. So now we will move on for K-forms. Oh, wait, no, the pullback. Sorry for that. Remember that a vector can be pushed forward by a smooth map, a vector. Vector fields cannot always be pushed forward. If you have a diffeomorphism, then you can push forward a vector field. Now, here we have the corresponding object for one forms, and it is called a pullback. Now, this comes from linear algebra. We will see first the linear algebra aspect of this. And the pullback of differential forms, it is used more often than the push forward of vector fields. Because remember, vector fields cannot always be pushed forward. A vector, you can always push it forward, but vector fields, not always. But for the pullback, that works on any differential form. Any differential form can be pulled back. So let's see the pullback first in linear algebra. So consider two vector spaces and a linear map between them. Then any linear map can be associated a dual linear map, but the direction will be flipped. So you see, it goes from B to W. The dual will go for W dual to V dual. The direction is flipped. And it happens that, in fact, F star is a linear map, and it is defined like this. So I take an element here. If I apply F, I get an element here. An element here is a linear map from B to the reals. So I put V here, and this has to be a scalar. And what is the definition? This one here. V is here, I push it to W by F, and alpha lies here, so it makes sense to evaluate. Okay? Is the definition of this map clear for you? So it happens that F star is a linear map. I'm not going to go into that, but you can check that this is linear. Okay? So this is the linear algebra setting. And now let's go back to manifolds and define the pullback of differential forms, but in this case, only one forms. But it will hold in general. So consider a smooth map between manifolds. Remember that for this, we have defined the differential, right? So we have this. This is a linear map. So then I can look at the dual, and the dual will look like this, right? So this goes here and this goes here. Okay? And so the pullback of a one form is defined like this. it is the same one as in the case of linear algebra. But so I take a one form here, and we're going to get a one form on M. You can see on M and on M. And it's given like this. Okay, so this is the pullback, and this is something very, very useful. Okay. Again, this holds for K-forms, but we will see it later. So far, we have only seen one forms. Okay. So now we go to K-forms. Before going to K-forms, are there any questions? Okay. Let me try to make a comment here. Let's see if you remember something like this. Let's say from calculus. And let's say that this f, let's put it 5. This 5, you should think of this as a change of variables. Okay. And then in calculus, maybe you want to if you want to use the change of variables, do you remember what do you do?
We take the expression, we take the derivative, then we just replace with the derivative.
So it will be f composed with 5. But what about the differential or how it goes?
It's going to be the differential of 5.
Like this?
Uh, with respect to x.
So look it up in your calculus book. And what you are doing so far is to pull back the one form. We don't say it like that, not in that language, but you're pulling back one form into the other. So go into your books and try to find this. So the idea is So let's say like this is where you want to integrate over this and also over this. This is your manifold. So I want to think of this as the change of variables, not as a real value function. And this is the real value function that you would like to integrate. Okay? So let's say you have here your variable s and your variable t. So in one way, you will try to compute the first one. Okay. But now, the other one, what is the relation between the two? So now you will compute using this. Okay. So this is supposed to be in here. So what is the relation between the two? What do you do when you want to integrate and you do the change of variables? To make things simpler, I just wrote it on R to R. You can do it on R2 even more explicitly from Cartesian coordinates to polar coordinates. But I mean, just with this, you will have an idea. And behind of this is the pullback of a one form. And that one form corresponds to this one and this one. And under this function. Okay. Right, so let's move on, okay? Or are there any questions or comments? Okay, so let's move on here. So again, for the time being, we can think of a K form as a function from the manifold to some space. This is what we will define later. So for each point, you assign this vector. Okay? This is the exterior algebra of this vector space. Oh, sorry, this is M. Right? So it's only that. So far, there's nothing there. And just to make it to be convenient for our context of differential geometry, I would like this function to be smooth, a function from M to the reals. If I take any k vector fields, because at each point this lies here, I can evaluate and get a number. And I would like that function to be smooth. This is the same way that we define one forms. And note that we are getting away with C infinity without defining the corresponding vector bundle. For one forms, we did the same. We don't have that. But we haven't defined the cotangent bundle and showed that it is a smooth manifold. Just by requiring alpha x to be smooth. So that will be a K form for us. And again, we will use very much our dx1, dx2, and so on when we look at the K-form on U. So how can I look at a K-form on U? I have a chart, coordinates x1 up to xn. So from a proposition below, we know that this is a basis, right? This is what we saw before. I'm writing this just to avoid writing all of this. And I have a basis. Now, from what you know from chapter 1 or multivariable calculus, if I have a basis here, I get a basis for this vector space. And that is using the wedge product. This collection turns out to be a basis for this vector space. And in fact, this is how you get the dimension that we discussed yesterday. Here, there are n choose k elements, which is the dimension of that vector space. Okay, and well, we're not going to use this, but if I have different coordinates, how do they change between one and the other is something that it is interesting to see, but I'm not going to cover that here for today. So locally, if I have a K-form on the chart, the K-form looks like this. Okay? The coefficients are smooth functions on U, and you also have, I wrote it here in short notation, but this stands for this. So this is how a local one form looks like. Only on U. And now let's go and define the corresponding vector bundle. Same argument as before. I define this to be the collection of all of these vector spaces, the k exterior power of T star m. And I already said I will use the same notation. We have the projection map. And again, I only have a set and a function. We will make that set into a smooth manifold, and everything together will be a vector bundle. Again, you can ask yourself, if I take a point here, what is the pre-image? And it is a vector space, and it is this. It's going to be a vector space of dimension n choose k, and corresponds to this vector space. Okay, I'm not going to review the smooth structure, but by now you can imagine how would you do it. You take a chart U, and on U, you know the description of a K-form, and that will help you to have let's do it. So you have U, Xn, this is the chart on M, and then you have this, right? So this is a point and a differential form on U. Oh, sorry, this is now a number. But now here is R and choose K. And the corresponding AIs, okay? Yes, I mean, they are not in order, so I don't know how to write it down. But there you would have the AIs. Okay, so in that way, you can compute the dimension of this. You have it like this. And again, it makes sense because you have n parameters to move along the manifold and n choose k along the fiber, the vector space. So that's the dimension of that manifold. Great. So questions? So in that way, we will think of this as a smooth manifold of dimension n plus n choose k, and all of this a smooth map. Moreover, it is a vector bundle. And so precisely a section of this vector bundle is a K-form. And the standard notation of the space of sections, we use this, omega. Okay. like this. So this is the standard notation for differential forms, differential K-forms. Sometimes we also say a differential form of degree K. That's also used. Okay, now the convention for this omega, these two we didn't use, and that's what I would like to try to define. Omega 0 is just the space of smooth functions, okay? Omega 1 is the set of sections of the cotangent bundle. And then omega 2, two forms, and so on. And remember that this stops, right? It doesn't go to infinity. Because this vector space vanishes when k is greater than the dimension of the vector space. So we go all the way up to n. Okay, so smooth functions, a different notation, 1 forms, blah, 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 up to n forms. Great. Any question? Now, I want you to understand why did we first study 1 forms and then k forms, and not we didn't do everything together. The whole idea is here, right? Sorry. We already know that that's a basis, and that help us to create this basis, and as a consequence, we have a description of K-forms. That's why we stick with 1 forms. They are like the building blocks, and then we constructed the rest. Okay, so the pullback is the same as we did before, but instead of a 1 form, you can put any other form, okay? Keep in mind that the direction is reverse. We have a smooth function from m to n. Then I will take a k form in n to a k form in m. And this k form is defined exactly as you expect by this formula here. Okay, so in general, any K form can be pulled back. So this is very important. We will always do this. The pullback of differential forms is fundamental, and you should know very well the definition. Right. Questions or comments? Now, I thought that was enough, but I want to continue with the differential. Okay, now first I would like to remind you this in Rn. Because in Rn we have global coordinates. So I will give you the formulas in Rn, and then next time we will see it on manifolds. And there, I'm stopped, right? I reached the dimension, and there's nothing more. Now, this is something fundamental. We have a differential, which we will write d, and it's going to be a function that takes a k form, and it will give me a k plus 1 k form. And this is called the differential, or the Ram differential. Okay? Now, so let's define it first on functions. I want to do it in Rn. Again, I'm doing this in Rn because we have global coordinates. So, if I have a function, so this is what I was trying to emphasize before. Before, df was only one thing, and here it is two. So this is a one form. And the whole idea is it should be exactly what we had before. Okay? So this is precisely the partial derivatives like this. Okay? Great. Now, in general, what it is. Let me take a K-form, but only with one summand, not multiple of them, only one. So I have a function like this. And what is the differential of this? Okay, assume that this is alpha. What is the alpha? Okay, let me write it down here instead. The alpha is the following. Basically, I'm just going to affect the function. Here I have a function and all of this. So the definition of this is, it is basically okay, what we had before. Right? And you can expand it if you want. And now the wedge product distributes over the sum. So and that's it. Okay? Now, many of the summands here are going to vanish. Why is that?
Because dxa, dxj might appear.
Right. If here I have a dxj, everything vanished. Okay. Now also note this, because I have k and one more, so it is k plus 1. Right? So in fact, I'm getting something like this. And the final thing about the differential is we will require to be linear. So the differential of a sum is the sum of the differentials. Because remember that we have here a sum. I define it only on one element, but here, and in that way is globally defined. Okay? An N form, how can I write an N form? What is the formula for an N form? And that's the general formula for an N form because there's only one summand. I cannot have many of them, right? F is a smooth function like this. So it's not Fi and all the rest, only one function. What can you tell me about this? The differential of that N form.
Should be 0.
Why?
Because again we got one repeated.
Right, because here all of the elements appear, right? I have dx1, dx2, dx3, all of them. So once that I compute the differential of this, a dxj will appear, but because all of them are here, I will get 0. Good. So this is 0. Okay? Right. Now, let me make the following definitions. And this is going just to tell you that this might seem new to you, but it's not new. You have seen this also in differential equations. So all of the forms whose differential is 0 are called closed. like this. So a differential form that isn't the image of D is called exact, and the ones are called closed, the kernel. Okay? So the kernel, the one that's moved to zero, the kernel are called closed. The ones that are on the image are called exact. Right? Now, let's work out the following problem. This will be done in R2 only with coordinate x and y. So consider a one form. I'm also going to give you away the answer with my notation. I have a one form here, right? Now, so this is closed if and only if the alpha is 0. And that's equivalent to what in terms of the functions p and q?
The partial of p with respect to y is equal to minus the partial of q with respect to x.
Right? And do you remember something like this?
Green's theorem.
Pardon?
Green's theorem.
I don't know. When you are, oh sorry, come back. Which one?
Green's theorem.
Green. Exactly. It goes along the line of Green's theorem. Right. Yes. Green's theorem, and also when you look at when you are solving differential equations, if the differential equation is exact, you can solve it. And that's the second part of the problem. So alpha is a one form. It's exact if it's the differential. So I have to put here a function, okay? A function. And this is equivalent to what in terms of P, Q, and F? In terms of the function P, Q, and F, what is it?
Equals the being here partials of f.
So come again, please.
P is the which one? Partial with respect to x, f,
Mm-hmm.
and q the partial with respect to y.
Wow. Right. So that's correct. And then now, so this ends here, okay? That's right. But then when you were solving differential equations like this, you will call it exact, but it was only on P and Q. You didn't involve any F. So how do you get rid of the F if you have this? The partial of P with respect to Y equals
the partial of f with respect to x with respect to y.
and then
Mm,
I want the function Q.
oh, the
If f is nice enough, we can change the order of the partials, right? And get partial with respect to x of q minus.
Q and X.
Yeah. No minus. Sorry.
Right? Which is very similar to that one, right? There's a minus there, here there's no minus. But I think when you were solving this in different, you can only solve it or you find a method to solve it if the differential equation was exact. And by exact, they meant something like this. So again, homework and look at that part of differential equations. All right. Any questions? Okay. Now, I hope that this problem was enlightening. I mean, there is many things that we have covered. Vector bundles, charts, and everything to talk about differential forms. And then we will see even more things because we need to define the differential on manifolds. Here it is only on Euclidean space. So you have differential forms and the differential. But all of that is the perfect language to write down an equation like this. So differential forms and the differential is a compact way of writing down a whole system of differential equations or partial differential equations. Just in a very, very short way. And then For instance, if you have heard physicists, when they talk about field theories or any gauge theory, they are basically using this type of language, things like this that you see here. So the equation that they write, they use this language, and because they're using differential forms and equations among them. So this is in part the differential in Euclidean space. We still need to see a couple of more aspects of this in Euclidean space. But I just wanted to jump and give you some applications that they are in the setting of differential forms, but you have seen it before with a different point of view. Okay, so the time is up. If there are no more questions. So we will meet on Wednesday at 10, right? The makeup class, right? Okay. So if there are no questions, see you on Wednesday at 10.
So yeah.
All right. See you Wednesday.
See you, bye.